All right, so blade angle, the difference between the chord line and plane of rotation. But pitch,
The
amount of something.
Pitch is relative to
big bite.
Pitch is how far the airplane moves forward in one revolution. I know.
That's so much.
So it's like a fine thread screw or a coarse thread screw. Now, some of you don't know the difference between a fine thread screw and a coarse thread screw, but hardware has different pitches to it. And it's another class. You can take that one. Oops, I don't want to show you that. All right, due to pitch distribution and twist of blade, the blade angle at one station is usually different from the blade angle at another station. The only time it would not be is if they're really close to each other. Twist of blade, the blade angle. At one station is usually different from the blade angle at another station. Blade angle has a pronounced effect on the mass of air moved as well as engine RPM. Ooh, that's something to unpack there. Blade angle has a pronounced effect on the mass of air moved as well as engine RPM. One degree of blade angle can change RPM by 60 to 90 RPMs. All right, blade angle has a pronounced effect on the mass of air. Okay, that's the thing. As well as engine RPM. So right now we're talking really about fixed pitch propellers. But you can take any propeller and just think of it as a fixed pitch, not moving. And by fixed pitch, of course, I mean that the blade angle doesn't really change. But see how we just call it a fixed pitch? Okay, so we could call it a fixed blade angle, but it doesn't sound right. So we say fixed pitch propeller, which is still true. When you are working on an aircraft with a fixed pitch propeller, one of the things you have to do on an annual inspection or 100-hour inspection is to determine the, do you guys know this one? Static RPM. So static RPM is what RPM the engine will achieve with the aircraft not moving forward. It has to be in the chocks and blocked. So you'll actually look at the type certificate data sheet. That's where it's going to say it. It'll tell you what propellers belong on the airplane, because there's usually a combination and there's usually a range of blade angles that you can have for each propeller, usually by about 3 to 4 degrees. And they'll call it pitch though. So, and then you run the engine up wide open throttle, carburetor heat off, mixture to best power, and your maximum RPM is called static RPM, which is an indication of two things. If it's the correct propeller, it is an indication of engine health. If it's the wrong propeller, it's usually a time that it'll tell you that, because it'll either overspeed or underspeed, but I wouldn't rely on that.
This whole thing, this is a fixed pitch prop thing?
Mm-hmm. Fixed pitch. Has to be fixed pitch. Well, I'm glad you said that, because probably somebody else didn't either. So yeah, you didn't. Okay. So doing the annual on the 150, right? And so feet on the brakes, wide open throttle, carb heat off, mixture should be at best power, which it usually is around here, wide open throttle. And I'm going to see where the RPM goes. Now, if you consider that the RPM, the tachyometer, is say redlined at 2,700, or this one I'm working on is 2,550, and the RPM comes right up to 2,000.
Would it not go? Would it not redline?
It will not. A fixed pitch prop should never redline on the ground, brakes locked, ever.
Why?
And I'm going to show you why, but it's because the blades are stalled. And they're hitting it like a paddle.
Wow, because the incoming error.
So it's hitting it. It's like the angle of attack is like flat against it. You don't realize that, but it really is. You think it's like this, but it's really a stupid angle of attack. And it's not like that really, but it's a bad angle of attack. So you have this paddle out there that's not an airfoil, really. Actually, it's instead of hitting, wait, yeah, brought it in here. So you think it's hitting it like this, but it's not. It's hitting it like this.
So does it sound like shit?
No, you don't notice a difference. It's a normal sound that you hear. So we don't think anything of it, but it tells you your engine health. Now the interesting thing about that is there's not much variation between, well, wait a minute, what if I then go up to Denver and do it there? Am I going to get the same results? Well, as long as you lean it out for the altitude, yeah, you're going to get about the same results. Because when you at a low altitude, you have thick air, so the engine's happy, but the blade's got thick air, so it's fighting harder. You go up to thin air, the engine's not happy, but the blade's got thin air, so that equals out. So it's almost the same across the board. So that's called static RPM check.
I don't get when then. So if it's stalled, then what if you cut the brakes, cut everything loose, it would go forward, right?
Mm-hmm.
So, but if it's completely.
It's not completely. There's enough thrust to move you, but it's really inefficient, horribly inefficient. As we're going to see, a fixed pitch, this is a constant speed, but a fixed pitch propeller is really only useful in a very narrow range of RPM and forward speed. Anything outside of that narrow range becomes inefficient. But I'm going to show you that in great depth to the point where you're like, I wish you wouldn't have shown me all that. So the reason why blades have pitch distribution, which is twist, and many different airfoils, is because the blade moves in multiple dimensions. So this is a real propeller, right? Take a look at it. I'm probably off camera, nobody can see it. But if I put it here and it falls at me in the head. So we can just see right off the bat that it's not completely square, right? This is narrower, this is wider, then it gets narrower down here. Look at it this way, we can see the twist, how it twists. You can see that down here it's fatter, up here it's much thinner. So it's just different in every different little plane. So they had to come up with that. Ooh, I could actually put that right there. Nobody would care, huh?
No, it's fine. It's fine.
I didn't think about the fact you can't see the board.
Yeah, you think about that every day.
Well, I put the chair down.
So if you just look a little to the right.
All right, let's see. Many different planes. Where am I at?
Womp womp.
Okay, what are my different planes? Different rotational speeds of each station. Can I just say different RPM at each station? And save time, SeaWorld?
Why not?
Why not?
Same rotation.
There's the same revolutions per minute of every station. Right? I'm gonna swing this around like big time. So if it's going around, right? It's all the same. I'm not gonna do that. It's all the same per minute, but once one piece of the propeller, the outer edge, is going a lot faster in miles per hour than the inside. Yes.
I don't understand.
That was one.
I guess that would beat the shit out of you now.
I know, he's a clump of man with a long
Bring up the ear.
Yeah, now.
It's got the dunce hat on, I believe.
No, it's the, you gotta get it.
I often talk about propellers as a plane of rotation. And I think about it as a solid disc almost, the propeller disc. So you can think about it the same way. But if we do it like this, just watch right here in the hub how slow that goes around. You can see every single rivet, right? Now try and do it up here. It's moving a lot faster. Miles per hour wise, this is really going fast out here.
Got a longer distance to travel to get back to the original too.
And the further out I get, the faster it's going to go. So out here, it's turning a lot faster. In here, it's turning a lot slower. Speeding up, speeding up, speeding up. See, I mean, just, I don't know. Yeah, try and count the spokes.
Pass it around.
You can't, but you can in the middle, right? You can see you can see the little rivets.
Yeah.
You can watch each one. And
Yeah, you're right, there's 36 spokes total.
there's 38.
No, there's not, there's 36. I counted them while you were doing it.
He knows bikes too well. He's probably- I will not challenge him on that one. All right, so different rotations, got it? But it's the same revolutions per minute. Okay. Different rotational speeds. And then forward movement of the aircraft creates different angles. I'm going to show you that. Forward movement of aircraft creates different angles. Creates different angles. Oh, angles of attack. I knew something. Angles of attack for each station. What's angle of attack?
Oh, it's the relative weight against the cord line.
All right, angle of attack. I'll write it here so we don't forget. Is the angle between the what?
Cord line and the cord line.
Chord line and relative wind. All right. It'll probably take me hang on. This could go over here like this. We can make this bigger. There we go. All right. This will take a second to let your kind of mind wrap around it. Sometimes it takes me a minute to do that. Laser pointer. All right, so this, I can't remember if this is the same blade. I think this is the same blade per, hang on, let me see. Angle of attack, ideal angle of attack is 2 to 4 degrees. And I'll write it later, but angle of attack needs to be 2.
What the?
Did this the other day. It's really obnoxious. I'm obviously doing something. Angle of attack. I hate you. All right, you just have to take my word for it. Angle of attack is 2 to 4 degrees. I must be doing something near the top. Is 2 to 4 degrees. Okay, got it. Woo. All right. 15 degrees will result in a stall. Blade angles are smallest at the tip and largest at the hub. We know that one. Okay. Is this the one that does that? Let me see.
I'm sorry, what did you say?
Hang on one
Angle
second.
was it, Sal?
I'll write it in a minute. Okay. So let me show you what this is about. And it's a good, don't freak out about it, but I think it's a great explanation. So what this is an example of an aircraft that is at 2,000 RPM, a blade at 2,000 RPM, moving forward at 150 miles per hour. So we just got one blade flying through the air, 2,000 RPM, doing 150 miles an hour. So at station at A, right here, A, this is at station 36. And what does that mean? 36 inches from the center line. Okay. This is at station 24. That is 24 inches. And this is at station 12. So this one's out at the tip. And this one's near the hub. Got it? Okay. So for every, so what we're doing is, they did, I'm not going to do it, Pythagorean theorem. Remember that from electricity? Yeah. Okay. So for every 1 foot the plane moves forward, and everything on the propeller is going to move forward all together, right? It's just spinning. So everything moves forward at one foot. Only difference is, this is easier, propeller spinning. So at 12 inches, we'll say it's right here, 12 inches, it is traveling, by the time it takes to go 1 foot, it went from here to here, right? And if I measure that, it only went 0.97 of a foot. Everybody follow?
Yeah.
Everybody follow? The propeller moved forward how far?
1 foot.
1 foot, but it's rotating. And so this spoke right here, but you have to think it's much bigger, went this far. Got it?
Mm-hmm.
So if I measured from here to here, that is a measurement of 0.97 of a foot. See that right there? 0.97 of a foot. Everybody got it? 0.97 of a foot. But I measured the same thing up here and it goes the same distance. It had to travel 1.94 of a foot. But I measured out here and it went the same it went the same angle.
2.9.
It moved 2.9 feet. So you see how that works? But we just have to enlarge it to a different scale. And at the time it took me to go forward 1 foot, it moved right here. Moved just see, it just moves a little bit by my hands, right? It only moved 0.97 of a foot. Up here it moved a lot more. It moved 1.94. Out here it moved a lot. 2 feet. You see that? Okay. So then you use Pythagorean theorem. Remember that? A squared plus b squared equals c squared. And you come up with an angle. Right here. Come up with this angle. So that's all they did. So somebody sat there and they figured out, all right, it's going to move forward 1 foot. And measure it. This part went almost a foot. This one went almost 2, and this one went almost 3 feet. Would have been easier if they would have did that, but could have just done that. Everybody follow so far? That's all they did. Somebody said, all right, airplane moved forward 1 foot. We'll make that line go this way for no particular reason. And it went this way, almost 3 feet. Well, we'll just draw that out at 3 feet. And then because of Pythagorean's theorem, which you guys know, they were able to figure out how long the hypotenuse was, which isn't important, but we can use our tan, sine, cosine, and figure out the angle. And they came up with an angle of? 19. So if they did that and they came up with an angle of 19 degrees, and I need my angle of attack has to be somewhere between 2 and 4, what do you think they want that angle to be then? I'm not sure if it'd be less or more in the way they drew that, but about 19 degrees, plus or minus 2. Follow?
Sure.
This is the relative the angle of attack. So if let me see.
Yeah.
90 degrees is your angle of your.
That's the angle of the hypotenuse. That's the angle of the relative wind is coming at.
Sure, and the ideal is 2 to 4.
And this needs to be 2 to 4 degrees off of that, a little bit more. So I guess it'd be.
You're saying 2 to 4 degrees off of 19, not 2 to 4 degrees to angle of attack.
If it was if the relative wind is coming out at which angle?
19 degrees.
19 degrees. So if the blade was at 19 degrees, my angle of attack would be 0. Don't want it 0. So if I do it right, then it would be 21 to 23. So blade angle should be 21 to 23 degrees if I did that right. Either that I'm doing it wrong and it should be like -4. But all right, so this one's at 27 degrees, so this angle needs to be 31, and this is 46 degrees, so this blade station needs to be 48 to 50. Follow?
Sure.
So that's how they come up with that.
No, I've been thinking with this, you're saying the blade angle when it's static?
Not static. This thing is moving forward.
Right, so,
We're moving.
right.
We're doing how fast is the airplane going? 150 miles per hour. Okay, go ahead.
Okay. I'm just not understanding this 2 to 4 degrees ideal angle of attack. Is that you're talking about 2 to 4 degrees off? I don't really understand where you're getting at.
So
I
imagine
had an idea, but now I think it's wrong.
a wing. We'll make it simple. Here's your wing going through the air. Angle of attack. Do you want a zero
Yeah,
angle of
zero.
attack? Or
You
do you,
only want it 2 to 4 degrees.
you want
right?
2 to 4 degrees?
Okay, so that's what I thought. But this whole 2931 shit's probably.
Well, that's because it's not a wing going this way. It's a wing going this way and forward at the same time.
That'd be like the angle of the bite, the pitch, the propellers take.
Yes.
pretty much?
It's doing this.
Yeah,
Where-
So that if you go back to the page right before,
This one?
yeah, that one. So the hypotenuse angle of hypotenuse to the
Uh-huh.
vertical axis.
Yeah,
That
up here.
would be that would be where where the wind is hitting the prop.
Yeah.
So that's where the wind is hitting the plane of rotation of the prop.
That's the angle of the wind at that spot, space.
relative to the plane of rotation.
Yes.
Okay. So
No, not relative. No, it is the angle of it. That is where the wind's coming from. It's coming from 46 degrees.
Wait, now.
The hypotenuse is the line of relative wind.
At B or at the SC.
Yes.
Okay, so then the 2 to 4 degrees would be.
You need the air to not hit it dead on,
Yeah, I understand.
but just a little bit off,
Yeah,
right?
So,
Or even if you want to do it this way, let's just say for 1 minute, we just want the air to hit straight on. We want this right here to match that what's written. It's an example of why it's twisted. That's the whole point of this. Why is it twisted? Because as one section moves forward 1 foot, so remember it's going, it's going this way. So everything is changing. This is not going this way, it's going this
yeah,
way.
I understand.
And it's going down and forward at a pretty fast pace. Down and forward. This is going down and forward at a less pace. So because it's down and forward, it's actually kind of going like that. Not this way like a wing, but it's going at an angle. And what angle is it coming at? Well, according to this one, out there on the tip, it's coming in about 19 degrees. Yeah.
So the tip has to be at a shallower angle in order to compensate for the rest of the blade, basically, since it's shallower, and it's moving a lot faster at the tip, it needs to be at a shallower angle since the rest of the blade is. I'm so sorry about that.
Yeah. Well, if you're just going to ask Suri, don't worry bother me for. Yes. Follow? Yes.
So if it's supposed to be like 2 to 4 degrees, why is it 19? Or
What should they have wrote?
I don't know, but like
They should have wrote 2 to 4.
You got to pick a number.
Okay, but that's just what,
That's the angle of the wind hitting it, right? Hang on. Let him finish before everybody starts.
so because you wrote the angle of attack is 2 to 4 degrees, so like where did the 19 come from, for example? Or
The 19 came from the fact that Pythagorean theorem says if this is 12 inches and this is 2.9 feet, which is whatever inches, 36 inches, then this is the angle you come up with. It's just math.
So 19 is just the zero out. Just 2 to 4.
Yeah.
from
And
there
what
you
I'm
go.
worried about is everybody's focused on the wrong thing. You've completely missed what I'm trying to explain to you. What I'm trying to show you is why is the blade twisted and not just straight?
Because it moves at different speeds.
It moves at different speeds, at different elements. And so if you want to forget about that and focus on this, go, well, I don't understand numbers. Well, I guess I'm sorry about that. I told you were not going to like this when I went into this slide because it's difficult to understand the numbers. Once you've done it a while, there's probably the simple. It's super simple. I said it's just Pythagorean's theorem. We did this. Resistance, impedance. No, impedance over here. So hang on, he's been waiting.
So the tall, the CB line is the where you're measuring from the root to the blade tip. So
That's how far it traveled.
that's the distance of travel.
Yes.
Oh, okay.
Around like
Yeah. Okay, so
See?
it's going 1 foot forward, and it's going 2.9 feet around.
This went 2.5 feet that way,
Yeah. Okay.
right? This went 2.5 feet this way. How far did this one go?
Less than half that.
1.94.
About 1.9. How far did this one go?
About
1.97.
Right. See? The whole thing's going how many RPMs?
2,000.
2,000. I'm going forward at 150 miles per hour, or 1 foot.
In so many seconds.
So yeah.
So is this why fixed pitch is very inefficient at multiple ranges?
You got it. So I've got to select one angle for this fixed pitch propeller. And now I'm not going to do it, but what happens if I slow down, I'm only going 80 miles per hour?
Now your
Then-
blade's all different.
Then I've set my blade angle at some number. It's not movable. And so how efficient is it going to be now?
Very.
All right, I think the next slide is,
Oh, man.
it kind of shows that. I don't know, maybe I should have went one way or the other, but just look at it right here in this slide right here. Here's the blade, right? And I'm start the engine up and I got my feet on the brakes. Here's the relative wind on that blade. Is that efficient or inefficient? And let's say this is 150 miles per hour and this is 0. So that is super inefficient. Well, how much better is it going to be at 10, 20, 30, 40 miles per hour? Completely useless. And so this would be halfway between. I'm going 75 miles per hour.
So you still have some inefficiencies with that.
Very inefficient. All right, that's just taking into consideration the RPM. What if I take into, now I got to add in, I did speed. Now I can factor in RPM. That changes it too. So everything is all kind of jacked up. No, I was right about
Now
that.
I'm getting why those engines have a placard about more efficient RPMs and stuff.
Right. So this is, again, a fixed pitch propeller. They're not efficient except for one narrow band of where they operate. If it's perfectly, and they say, oh man, this prop is designed to run at 2,400 RPM. You're like, great. But you also have to go 110 knots. Well, what if you slow down and your angle of attack, you put the flaps out or something like that? You just lose efficiency. Yeah.
Is it always just that, or can they adjust it? Well, it's like, well, if you're at 2,100 RPM and you're going whatever
Nope.
speed, then it.
I don't think it does. I don't think it does.
You can adjust on the ground with a hammer.
I'm sure I could, but I mean, like, I wasn't sure if there was a way where you could just.
Well, as long as you can do that, Pythagorean's theorem, and
That's-
figure it out. But
That's a lot
but
of work, though, and I don't like that.
but you got to get that 19 degrees. How are you going to get the 19 degrees if you shorten this? What would you have to do?
Get a longer
Lengthen the.
No, I think you
shorten that.
you shorten that.
Yeah, so
Yeah.
you'd lose.
So
RPM.
slower and less RPM.
So almost like when you're coming into land and you.
Yeah, so that'd be efficient, but you're going to lose horsepower, so that
Yeah.
falls off there. So when you go to take off and you push the throttle forward, you are
Losing efficiency.
horribly inefficient. And you start rolling and you get more efficient, more efficient, more efficient until you get to your efficiency point. Then you exceed it because you're taking off and you're going to redline RPM. So I told you a second ago, when you have your feet on the brakes with the fixed pitch propeller and you throttle forward, it's called static RPM. It's a published number in the type certificate data sheet. You've got to hit it. Not less than, not above. What if you go less than?
No.
Engine's not producing enough power. What if you go over? Engine's producing too much power. Your pitch is too flat and you're going to overspeed. So when you go full RPM and you take your feet off the brakes and you're staring down the runway, you're going way past red line. Also, it's not an efficient prop for that engine. It wasn't set up for that engine. So, but you are going to exceed that little sweet spot, because you're going to red line nearly as you're going down the runway, so you'll lose some efficiency. Yeah.
You said if the propeller's going too fast, it's got less pitch, or it doesn't have enough pitch.
For that scenario.
If it's going too slow, the engine just doesn't have enough power.
Well, okay, let's say we take an engine that is perfect. I mean, it's a 150 horse engine, and we put it on a dynamometer and we tested it, and it's exactly 150 RPM. So if I put a prop on it that has too much pitch, see how I called it pitch, or the blade angle's too high, and I run it, RPM is going to be too low. If I flatten it out, then the RPM is going to be too high. So when I tested airplanes on a test stand, we needed what was called a test club. Remember those? It's a 4-bladed wooden propeller, fixed pitch wooden propeller. It was designed to turn at the one we use most often. Well, you're supposed to get one for each engine. So I was thinking about one in my mind that we used for the 200 horsepower Lycomings. So when you went wide open throttle on the 200 horsepower Lycomings, it went right up to 2,700. And that is max red line, and so that tells me that it was absorbing 200 horsepower. Because the engine put out 200 horsepower at 2,700 RPM, and that's where this thing went. So the pitch was designed to go right to 2,700 and give you that. So, all right, I don't think I'm going to write all the notes for this, because I don't need you to memorize this. What I need you to understand is why it twists, and try and see that in your mind. It's going around at a certain RPM and forward, so that around and forward gives, it's not this way and it's not this way, it's somewhere in between, and each little station has its own little thing that's going on. And then also this right here, we see, angle of attack will change with any RPM or aircraft speed. Let's see, what do I have right here? Yeah, this one I said. Note the difference between angle of attack when stationary versus in flight. On the ground, the prop moves from A to B. So on the ground, prop moves from A to B, right? Just A to B, straight down, because you're on the ground. Angle of attack is very inefficient. In flight, it moves from N to O, so it's going forward. And, let me see, aircraft moves from N to O, and blade moves from A to D, and that gives you a more efficient angle of attack. So, angle of attack E is efficient. Got it? Okay. That's what we need to know. I'll write a few things. So now you see what Orville was talking about? Why he decided to start making popcorn instead?
Yeah.
Is that what's burning?
Let's see. Okay, so I wrote that, angle of attack, core line, so let me see.
I get it too, though. There's just.
Oh, yeah.
But I totally get it.
Ideal of angle of attack is how much? 2 to 4 degrees. 2 degrees to 4 degrees. 15 degrees will result in a stall. I think you all know what a stall is. Blade angle is smallest at tip. And largest at hub. And why is that?
Because each section is moving at different speeds.
And which one's moving the fastest?
Tip.
Tip. Okay. That's a 6. The AOA will change with any change in RPM, or aircraft speed. Seven, fixed pitch props.
Wait, what?
Huh?
Where are we getting 6 and 7 from?
What happened to 3 through 5?
It was me explaining all those slides.
6 comes after 5.
Let me see. What exactly was it? 4, 5. Oh, no, the notes just kind of fell apart.
Like a.
The word, I swear, sometimes when I stop and turn off Word and start it again, it's like, why? So, just go with it. 7, fixed pitch props are typically
Cheaper.
designed for optimum efficiency at a narrow set of parameters.
God bless you.
I should fix my notes. Now I'm going back into pitch. So I see why constant speed props are far more desirable.
Yep.
Yeah.
So keep in mind that a constant speed propeller does not have static RPM. Why not?
Because it's constantly changing.
The blade is always changing. And so if I get into an aircraft with a constant speed propeller and I put my foot on the brakes and I don't move the aircraft and I mash the throttle, push the throttle all the way to the firewall, where does it go to the RPM?
Straight to red line.
It goes right up and touches red line. Now, how did they design it to do just that? They didn't. As a mechanic, you set the governor or the low pitch. You set the low pitch stops to let it overspeed. They do that at the prop shop, and then you set the governor, which we'll talk about coming up, to stop it right there. So the governor senses the speed and changes the blade angle to stop it at that red line. Yeah.
So then are you also looking at your manifold pressure to see the load on it too? To see if it's doing its thing correctly or?
Yeah, that you can do, because you won't do static RPM, but you can look at manifold pressure. But they don't give you that number, so it's like, and if it's all the way forward, it's just, again, the manifold pressure is kind of set. All right, let's talk about, I don't know, this is like big point number 3 way out here, pitch, which would make sense probably if we went all the way back through it. So pitch is often used as a synonym for blade angle, but it's not. Blade angle is what?
Angle of the blade relative to the blade.
Blade angle equals chord to plane of rotation. I don't know, think of blade angle as an actual angle. Blade pitch is the distance the aircraft will move forward with 1 revolution of the prop. So think of pitch in inches like pitch of a bolt or screw. Follow?
Sure.
Okay, so going back to our other slide where everybody's confused, Pythagorean theorem, what's our takeaway from that?
Twists.
It's twists.
Different.
Because it spins at different speeds, same RPM, different speeds, and the forward velocity of the aircraft. The two have to match up to create an angle, and the angle changes throughout the distribution of the blade. That's all we need to know right there. Got it? Right. But we need to know blade angle is the difference between the blade angle and the chord line. And how could you measure that?
With a protractor.
Do with a protractor. So with a and we'll look at protractors. Let me see. We're going to look at prop protractors here in a bit. Probably not today. Let me see. Prop protractor. Oh, this has the best video of all. I don't see a prop protractor. That's sad. Next week. Oh, there it is. No, it isn't. We'll talk about prop protractors at a different slideshow event. But it's just a protractor that measures an angle. So blade angle you measure with an angle finding tool. Pitch, you can't find pitch by doing that. You got to do maths to do pitch. So pitch, again, refers to
Distance here.
Forward revolution.
pitch is how far aircraft will move forward, assuming you're going forward, in one revolution. Well, how are we going to figure that out?
Math?
With maths, okay.
Ew.
So based on, but we got to standardize it, so it's all based on the blade angle at the 75% station. By the way, it's not just pitch, it's geometric pitch. Geometric pitch is the proper term. But you can just say pitch. I'm okay with it.
Is the 75 station like closest to the tip or closest to the hook?
So you would take the full measurement of the blade and 75% of that, so it's 3/4 of the way out. Now you don't measure in, you always measure out. Let's see, what do we got? Geometric pitch, because there's two types of pitch. So one is geometric pitch. It is, in fact, the theoretical distance, an element of the prop would move forward, I realize I'm being a little redundant, so you don't write it if you don't want to. In one revolution,
I think it just means it's important.
Cool, Phil says.
sometimes it means I stopped doing something because I got interrupted, sat back down on my computer, wrote my notes. I'm like, what was that again? Oh yeah, I should tell about geometric pitch. In one revolution, if it were moving along, a helix, that's a spiral. having an angle equal to the blade angle. That's a lot of words for saying it's how far the blade would move forward in one revolution if you took the blade station at 75% and you had a certain twist to it, and how far would you go forward if you calculated this out and we were like in a solid. So it's not accounting for any slip whatsoever, geometric pitch, which is what it's saying. So it's moving along a helix that has the same angle as the blade. No slip. Let me see. I think I give a couple of different formulas for doing this. Somebody said this isn't the same formula that I use in lab. So maybe before I do this, I'll get that lab one. Who's got their lab sheet? Geometric, we'll see what's different. Geometric pitch equals, 2 pi times r times tangent, of blade angle. Let me see. What's that?
That's just, I got pi times 0.75 times diameter times tan of blade angle, 75%.
Well, it's blade angle at 75% station. So that's kind of a given there. So you got to get it there. And then what did I do in your lab work? I guess it's the same. Oh, that's a little bit different.
But then it's still multiplied by 75%.
Yeah, so it's close. This is just, you have to get it at the 75% station right off the bat. The one I give you in lab is geometric pitch equals pi times 0.75 times, oops, I'm sorry. It is not, it just equals pi. Hang on, I was looking at the wrong thing. It's pi times 0.75 times diameter times tangent tan b, where this is the blade angle at 75% station, and d is the diameter of the blade diameter of blade. All right, probably a good place to stop right there. Because you're like, I don't want to do that.
It's been a long